In this video, we'll take a look at the hydroboration of an alkene, the addition of water, H and OH, across the double bond of an alkene. And this addition occurs in a syn addition and in an anti-Markovnikov manner. Let's take a look at the mechanism. In this example, we have a methyl cyclohexene and BH3. Now, the significant thing about boron is that it only has 3 valence electrons, and as a result, once it's hybridized, it will be sp2 hybridized, which means that we have an empty p orbital that was not hybridized. So the significant thing about BH3 is this empty p orbital, and this empty p orbital allows BH3 to act as a very strong Lewis acid. This empty p orbital will allow it to suck electrons in like a vacuum cleaner, but then the boron wants to spit those electrons back out. So when you have these two compounds in front of you, you ask yourself, what's the driving force? And it's this empty p orbital that's the driving force, making this a very strong Lewis acid. A Lewis acid is a strong electron acceptor. So this wants to accept electrons. Which electrons can it accept? We have a pi bond over here. These 2 electrons will get sucked in to the BH3, the empty p orbital. At this point now, we're going to have the addition of the boron. The question then becomes, which of these carbons of the carbon-carbon double bond will bond with the boron, and which one will remain as a carbocation? And the more substituted one would be the one that's better as the carbocation. The less substituted one is the one that's going to go ahead and pick up the boron. Now, the boron at this moment will have its 3 hydrogens and a bond. Now, this is contributing 4 valence electrons, which means it's negatively charged, negative formal charge, and the boron wants to regenerate its empty p orbital. So here we're going to have a 4-member transition state. That boron is just going to bend over and deposit the hydrogen on the same face that the boron was added. Now, let me make a note over here. Provided that there are no steric hindrance effects, the boron will add to either face. I just drew a wedge over here, but this easily could have been dashed. So now we're going to deposit that hydrogen, and we're going to have the following. The hydrogen added and the boron here. And the boron is happy because it has regenerated its empty p orbital. We've now added the hydrogen across the double bond right there. That's the hydrogen that we added. And at this point, the abbreviated mechanism is that we would go ahead and show step 2, hydrogen peroxide with hydroxide, and that mechanism is pretty complicated, but we could get into it, but we're not going to get into it in this video. And this would replace the boron, and as a result you would have ended up having, on the same face, it's not an SN2 reaction or anything like that. It's a mechanism that we would get into. And oftentimes that's acceptable to just go right to there. But let's take a look at what really happens. What really happens is now that this boron has its empty p orbital again. And guess what? We still have a reagent substrate in the beaker. So what's going to happen here is I'm going to redraw. Let me do this over here. I'm going to redraw that over here for clarity sake. So we have this compound, CH3, the boron with its empty p orbital, hydrogen, hydrogen, and this is the hydrogen that it added. And what's going to happen is the same thing. This is going to repeat itself. So I'm going to draw this molecule like that, and this is going to pull in that pi electrons from another reagent molecule and go through the same process and deposit a hydrogen on the same face. And so now I'm going to draw this over here. Here's this hydrogen, and this is CH3. There's the previous hydrogen. This is the hydrogen that was added. The boron now will have a hydrogen, hydrogen, and connected to this compound, another one of its kind, there we go, with the carbocation, and the boron is negative, minus one formal charge. It will deposit a hydrogen on the same face. I'll go ahead and make this wedged right there. And so now we're going to have that, and we've added the hydrogen here. There's our CH3. We have the same thing on this side, and here's our hydrogen there, and our CH3. And then this boron still has one hydrogen remaining, and now the boron has an empty p orbital. And guess what? It's going to happen one more time. It's going to suck in another one of these molecules. Here we go. Pull in that and give us our, I'm going to erase that right there. And give us, I'm going to draw two arrows here. We can go into more detail, but when all is said and done, you're going to end up with a boron. It's going to recoup its empty p orbital, and it's going to have three of these. And if this was wedged from the point of view of the cyclohexane, we've added the H there, and then over here, and there's a CH3. We've added the H over here, and the same thing over here. We've added, there's that, and we've added the H over there. So this is a little sloppy, but that's what's it's a boron with three of those cyclohexanes attached to it. And then the mechanism is such that we would add H2O2 and hydroxide, and that will basically oxidize and remove the boron from all of these. And when all is said and done, you're going to get this compound here where we've added H, and we're going to replace the boron right here, the boron in each one of these with OH. And we've done our Markovnikov addition. Anti-Markovnikov addition. So basically, when all is said and done, we really need three equivalents of this reactant and only one equivalent of the BH3. This will go ahead and make three of those molecules.